the very famous LIGO experiment. So I think we have spoken about LIGO before. I definitely remember, where it's basically a gravitational wave observatory. It's called a Laser Interferometer Gravitational Wave Observatory. Stands for LIGO.
I think we talked about it in the interview with Dr. Steinberg.
Yes, I think we did. I think we did talk a little bit about that. Yeah, it's a really cool facility. And, they have huge arms and stuff to basically detect gravitational waves. And in 2015, and this is a little weird, I was talking to Parker about this before, almost exactly 100 years after Einstein's general relativity paper, which was in 1915, they discovered these gravitational waves in 2015. And I just find, it's just a little eerie.
Which is actually like one of the predictions that has been confirmed, right? Mm-hmm. Because the theory of general relativity has several predictions, and gravitational waves is one of them. Mm-hmm. And so 100 years later, approximately, it was actually confirmed. Now, some things have yet to be confirmed, like white holes. We have not confirmed white holes. We have confirmed black holes, though, recently with the images of black holes. But even before capturing an image, theoretically, or I guess experimentally, we knew that black holes already existed because of the mass and the kinematics of galaxies around the centers. We could infer that something really, really massive and, not that big, quote unquote big, was lying at in the center.
Yeah, and gravitational waves are so important because, remember, Einstein predicted that basically he said gravity doesn't even exist. It's not a force, it's just basically space-time, right? And if you guys checked out our episode 51 with Dr. Saeed Rastagoo, super cool episode, where we were actually talking about how gravity is not a thing. It's not even, it's just a consequence of space-time curvature. So gravitational waves are not gravity, it's just space-time moving up and down. It's basically just oscillating space-time. So I don't know if we spoke about how they did the experiment, maybe just a quick rundown. So basically LIGO has two arms that are perpendicular to each other. And if a gravitational wave, in this sense, were to pass by Earth, it would be moving in one direction primarily, right? So it will be moving so remember, because gravitational waves is space-time that is moving, it's literally stretching and compressing space-time. That's space, basically. So when it comes to one of the detectors, it will shrink one of the detectors, one of the arms, more than it does the other, right? Because one is perpendicular to one and it's only going in one direction. So it's going to shrink one more than the other. So the light that is actually being reflected off of these arms will take different times to reach the photodetector.
Okay, but think about this real quick.
Yeah.
I don't know if you have the answer to this, but what if the two perpendicular arms are set up in a way as if they were the two top sides of a equilateral triangle, and then what if the gravitational wave comes in transversely, right? So then it would kind of affect the arms by the same amount. So how would it work?
No, but this is perfectly perpendicular, right? So it's literally two different... You can think about it like if you're thinking about X and Y, right? They're two different dimensions. So you're looking at two perpendicular dimensions. You're literally looking at two different directions. One that goes north and one that goes east.
What if it's like this? This isn't a very good audio description.
For the audio, yeah.
Okay. Okay, imagine it's like a tent, right? Like the two sides of a tent.
I understand what you're saying.
And then it sweeps out vertically like across. So it kind of affects each arm by the same amount.
I kind of understand what you're saying, but that won't necessarily be the case because of the speed of light and how fast these detectors are really detecting this change. So the moment the gravitational wave comes and shifts one of them, again, I'm probably, this is just my guess, obviously, I don't know this, but my guess is the moment the gravitational wave comes and shifts one of them, the other one is still going to be in sync. So the light that's received at the photodetector for that split second, which obviously it can account for, is because
So I guess now you can kind of comment on the accuracy of these detectors.
Yeah, I was actually just gonna say, like, a really cool
Yeah.
thing about LIGO is that maybe I can pull the quote straight from the thing, but basically, wait, where is it? Do I still have the quote? Oh, no way. Oh, it's right here. It's right here. Sorry guys. I'm looking for. Okay, basically he was saying the accuracy of LIGO is like measuring the width of a micron. So basically like think about the width of a human strand of hair. So a micron, basically, a micron thick, measuring a human hair at the distance from Earth at Alpha Centauri, which is about 4 light years away. So the accuracy is as good as seeing that piece of hair 4 light years away. That's
extremely
how accurate this thing is.
But, this is accurate in terms of human tools, right? Because we're never going to need that type of accuracy for measurements locally here on Earth.
Of course. This is just for extraordinary experiments, right?
But when you think about astronomical scales, this is actually, quote unquote, not that accurate.
4 light years?
Right? 4 light years is not that far.
Oh, nothing. It's
right?
Absolutely nothing.
Exactly.
It's nothing.
Exactly. So that accuracy, when you're trying to measure something that is, 20 billion light years away, it's not going to translate as well as, something that's 4 light years away.